Welcome. In electrical engineering, everything, and I mean everything, builds on the fundamentals. Today, we're diving into one of the most critical, the series circuit. And trust me, getting this down is the key that will unlock your ability to analyze much more complex systems later on. So here's what we've got on tap. We're going to start with the absolute basics of what makes a series circuit a series circuit. Then we'll build up our toolkit with Ohm's and Kirchhoff's laws. After that, we'll see how to handle multiple voltage sources. And finally, we'll put it all into practice with a real-world troubleshooting scenario. All right, let's kick things off with the basics. Before we can analyze anything, we need to be crystal clear on what we really mean when we say series circuit. You hear the term all the time, but it's that specific single-path nature that's going to be so important for all the math that comes later. The number one rule of a series circuit, the big takeaway, is this. There is only one path for the current. The best way to picture it is like a one-lane road. Every single electron that leaves the power source has to travel through every single component, one after another, before it gets back home. There are no exits, no off-ramps, no detours. And this is huge because it means the current is identical at every single point in that circuit. You know, any basic circuit has got to have three things: a source, like a battery, to provide the push, a load, like a light bulb, to do the work, and a path for the current to flow. In a series circuit, that path is just one simple continuous loop with everything connected end to end. So now that we've got the layout down, we need a way to actually crunch the numbers. And that brings us to the beautiful, powerful Ohm's law. This is the fundamental relationship that governs how voltage, current, and resistance all play together. V equals I times R. I mean, this little equation, it's the absolute cornerstone of all DC circuit analysis. If you know any two of these values, voltage, current, or resistance, you can always find the third. It's what lets us move from just looking at a circuit to actually quantifying exactly what it's doing. And you know, it's pretty cool to think about how the pioneers of this field laid the groundwork for everything we do today. It's funny, George Ohm actually had a tough time getting people to accept his work at first, but his idea was so essential that now we honor him every single time we measure resistance in ohm. Okay, this is where the rubber meets the road. We're moving from theory to actual design. Let's say you need to power an LED and it needs exactly 2.5 milliamps of current from a 3.3 volt source. Well, first thing we do, step one, is use Ohm's law to figure out the total resistance the circuit needs. A little division tells us that's 1.32 kiloohms. But what if, as you see in step two, there's already a 330 ohm resistor in there? No problem. In step three, we just subtract what we have from what we need. And that tells us we have to add a 990 ohm resistor in series to hit our target current. See, we're not just analyzing, we're building. Okay, so Ohm's law is perfect for looking at one component at a time. But what about the bigger picture, the whole circuit? For that, we need another key tool in our belt, Kirchhoff's voltage law, or KVL. And this law, it's all about one of the fundamental principles of physics, the conservation of energy. At its heart, KVL is just saying you can't create or destroy energy. The voltage source puts energy into the circuit, and as the current flows, the components, the resistors, use that energy up. We call that a voltage drop. It's like a toll the current has to pay to get through each component. KVL just says that the total energy you put in has to equal the total energy used by all the components. It's a perfect balance. Yeah, the best way to picture this is to think of your source voltage as a budget, like your monthly paycheck. As the current flows through each resistor, a piece of that voltage budget gets dropped or spent. By the time the current gets all the way back to the source, that entire budget has to be accounted for. The sum of all the little drops has to equal what you started with. And here it is, the math behind it. Look how simple that is. But don't let that fool you. It is incredibly powerful. It doesn't matter if you have 2 resistors or 200 of them. In a series loop, the sum of their individual voltage drops will always, and I mean always, no exceptions, equal the source voltage. This is a rule you're going to use constantly. Okay, so what happens if we start throwing more than one power source into the mix? You know, like putting extra batteries in a flashlight. KVL actually gives us a really simple way to figure this out. So let's talk about voltage sources in series. So it all comes down to polarity. Which way are the batteries facing? If you connect them the right way, negative to positive, like on the left, their voltages add up perfectly. They're helping each other out. But if you flip one around, connecting them positive to positive, like on the right, they actually fight each other. The total voltage you get is just the difference between them, with a stronger one winning out. All right, this is the fun part. This is where we put it all together. we've got the theory, we've got the laws. Now let's do what we, as engineers, live for. Find a problem and solve it. So let's take a look at this circuit. We've got a 10-volt source and 4 identical resistors all in a row. Now, using our laws, we can predict exactly what should be happening. Since all the resistors are the same, that 10-volt budget is going to split perfectly evenly across them. That means after the current gets through the first 2 resistors, exactly half our budget, 5 volts, should be dropped. And this is it, the moment every technician and engineer knows well. You put your meter on the circuit, and the number you see just isn't what you calculated. But that number, that 6.67 volts, it's not random. It's a clue. It's the circuit trying to tell us something's wrong. So the question is, what's the fault, and where is it? And a really common culprit for this kind of thing is a short circuit. This just means something, maybe a bad component or a stray bit of wire, has created a super low resistance path. You got to remember, current is lazy. It's always going to take the path of least resistance. So it just bypasses the shorted component entirely, which throws off all the voltage drops for the rest of the circuit. So how do we hunt this thing down without just randomly poking around? We use a smart, systematic strategy called half-splitting. Okay, step 1. Our first measurement of 6.67V was higher than expected. That tells us the total resistance of the circuit went down, so the short must be in the other half of the circuit. Step 2. We measure the second half, and bingo, the voltage is low. That confirms the fault is right here in this section. Finally, step 3. We narrow it down. We measure R3, and it's fine. Boom! By process of elimination, R4 has to be our shorted component. That's logical troubleshooting right there. Okay, so let's just pull all this together. First up, that single path. It means the current is the same everywhere, no question. Second, resistances and voltage drops just add up. It's that simple. And third, Ohm's law and KVL are your power tools. They let you calculate exactly what a circuit should be doing, which is how you spot a problem when it's not. These are the tools that are going to stick with you for your entire career. So we have totally mastered the single-lane highway. But let's be real, most circuits out there are more like a crazy downtown intersection with roads going everywhere. This brings up a big question. What happens when the current is given a choice, when the path splits? How do our fundamental laws hold up when things get complicated? Well, we'll answer that in our next explainer when we dive into parallel circuits. Thanks for watching.